thank you very much for coming along this morning. My name's Ben Marshall. Happy Valentine's Day, and because it's love your network and love your Wi-Fi, I have love heart shapes candies. So take one, pass it around, or take a couple and pass them around. I guess we've got a pretty complicated topic that I'm trying to break down to its simplest parts today, and trying to make it a bit of fun by doing something with the love hearts for Valentine's Day as well. So enjoy. Good questions, good answers, really, really bad ones, we might have some more hearts to give out as we go along as well, so enjoy. Yeah, they're vegetarian, vegan, everything's safe, they're just full of sugar, so. All right, thank you very much again for coming along. Now, because it's so complicated, I'm going to start from the very, very basics. Some of you will know this already, hopefully most of you will get the basics for this, and we'll go through it as rapidly as I can. If I'm going too fast past something or there's too much detail on something, let me know and I'll slow down and stop. And I'll try and ask you questions as we go through as well to try and break up the flow and make sure that you guys get the questions answered that you want as well. So when we're talking about networks, I normally talk about it in three ways. We've got the central concepts behind it, the actual hardware bits, and the software bits that go with it as well. So basic concepts, start with what is a computer network? Very, very simplest form, it's multiple computers connected together. So that could be 2, that could be 3, could be half a dozen, could be 5 million across the world. If they're all connected on a local network into one switch or into a single switch or into a network of switches locally, then it's a LAN. If you go to a bigger system, then you end up with something like a WAN, where you've got it connected to one network here, another network there, paired up and connected together, generally through routers. Okay, internet, obviously enjoying my 80s and 90s era stuff from this. Basic terms for parts of a network, clients and servers. Servers are something that has the gear that you want, and a client is something that requests the gear that you want. So that could be a web page, could be an image, could be documents, could be anything else like that. So in this particular scenario, we've got a phone that is the client, and it sends a request to the server saying, send me trafficcone.com. The server says, here it is. In a general sense, there are heaps of different ways that you can think about the same type of relationship. That could be the coffee cup to your stomach. You've got a server and you've got the client that's there. It could be a NAS drive serving up music. It could be an internet provider. It could be all sorts of other things like that for it. Simple enough. Server holds and supplies it. The client requests and receives it. As part of this, we've got a thing called a domain name system. So trafficcone.com doesn't actually exist. Actually, it really does, but it doesn't exist at trafficcone.com. What it exists at is 66.252.101.155. That's the IP address for that website as served by these guys that do it. So if I go to that address, I can type in the numbers if I can remember what they are, or I can type in the address itself, and then a DNS service provides the information. So the most common analogy that people use for this one is a telephone book. I might look through my list of contacts on my phone. I don't remember what Darren's number is, because why would I remember? But I can look through my phone directory and go, Darren Rowlands, hit the button and it'll call him whether I know what it is or not. So this is what a DNS service does. With something like Google, Google has, thousands, hundreds of different IP addresses that it has bought or registered and whatever else like that. So when you type it in, you don't have to remember any of those. You'll go to whichever one that Google thinks is the best one for you today based on everything else that they're trying to do. So the internet's phone book. Where this comes into importance for a normal LAN or something similar is if you type in a request like google.com and your DNS is a slow one, so it could be the DNS that's built into your router or on your network, a crap old server, or you could be pointing it at a server in Russia to give you the information for it. This server's bouncing to that one, to that one, to that one, to that one, eventually to somewhere that can help it and give you the right information and bring it back out again. There are lists of publicly available DNS services. You might want to choose a better one for your gear to make it faster, and that might speed up your web browsing. Just takes away one extra step between what you're doing and what's going on. Probably one of the better ones is 1.1.1.1. So if you do want to try it out, you can for yourself. All right. A MAC, a PHY or physical address. So every network component has a physical MAC address. Physical, MAC, they're all equivalent names to the same thing. These are hard-coded to the hardware, essentially, when it's built. So your network card in your computer, your Ethernet adapter that you plug in your mobile phone, all has a MAC address on it. And it's a unique identifier for that piece of hardware. In a local area network, it's what's used to route the traffic around. It's not based on the IP addresses, it's based on the MAC addresses of the actual hardware itself. It's easier and shorter to do. So on this network card, it's 00130200B2 for an example. They're always in the form XX:XX.XX and so on, where they use hexadecimal numbers for each of the ones that are there. And obviously there's your binary to decimal to hex table, just for those of you who can't remember that D equals 1101 in binary. There are over 241 trillion possible MAC addresses, which sounds like a lot, and they reckon they'll run out in about 2080 or so because of the number of devices that we just keep adding to the network. The phone, the laptop has multiple Wi-Fi cards, so it has multiple MAC addresses basically built into it. Bluetooth has a similar sort of addressing system. Every Internet of Things device that connects to the internet, everything has a MAC address for it. So we're going to run out of these pretty quickly. Probably sooner than 2080, but we'll see how we go with that. In the other thing that we need to know, and this is probably one of the biggest ones, is an IP address. So a MAC address is the physical address of the device itself. The IP address is something that's assigned to it by the network, by the router, by the switch that's doing DHCP, there are other components that are on the network. An IP address is how a device is located on the grand scheme of the internet. When you've got an IPv4 address, I'll get to IPv6 in a minute, we look at in a decimal form, so 172.16.254.1. It's actually based on a binary thing. Binary equals this, and there's a hex version of it and other things as well. But a 1 is 000000001, and all the other ones as we go on and along. So this is how we get to the 2 by the 32 possible addresses. Every single one of these positions, and there are 32 of them, can be either a 0 or a 1, which means there's 2 to the power of 32 possible addresses based on that. The other thing that comes out of this is each octet, or each 8-bit part of this, has a maximum value of 255, sorry, I've written that wrong, 255, and a minimum value of 0. Does anybody know why that is? It comes from the binary. The simple thing is, when you count up from 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on and so on and so on, there are 255 of those possible from here. So each one of these can go all the way up to 255, and you can see it there from range to range. 2 to the power of 32 means 3.7 billion public IP addresses. Putting aside the reserved ones for now, these are the ones available to any router that goes onto the internet. That's any device that connects directly to the internet, not your phones, not your tablets, the actual routers that are sending it there. Those 3.7 billion are often dynamically assigned, so Telstra will buy a whole big chunk of IP addresses, a whole big bank of them, and say, I've got 10,000 customers now, we expect we're going to have 20,000, let's buy 25,000 IP addresses or thereabouts. And then as you connect to the network or not, your IP address is assigned dynamically by Telstra. You might keep it for a week, a month, a year, but at some point, if your router goes down or drops off, your IP address, your public IP address will change. Okay, this is one of the things that CCTV guys in particular get stuck on, because what my IP address appears to be in the world now, where I want to go and look at my cameras and dial into them and dial into my system remotely, that IP address can change that quickly between Telstra deciding now that you're on this and now that you're on that. Has anybody had any experience with 3G, 4G, 5G, etc. routers? Do they keep a static IP address or a dynamic IP address? What do you reckon? No idea? Most commonly, it's a dynamic one. And every time you disconnect and reconnect to the tower, you're getting a brand new IP address every single time. So I know Joe had a customer that was doing something with houseboats a very long time ago where they wanted CCTV systems on them, wanted to view them remotely. The only internet access they had on the houseboat itself was a 3G, 4G modem, which means every time that power went off to that, or they changed towers from one to the next one, went out of range or whatever else happened, the public IP address changed and it made a mess of everything. There's a slide that I haven't actually put in here on dynamic DNSs. So remember before I talked about a DNS as something that translates between google.com and an actual numerical address? A service like NoIP or dynamic DNS, and there are a heap of other ones, you can roll your own and build your own in the software, acts as that translator for you. So instead of going to Joe's cameras, going to 72 dot whatever for Joe's cameras, you're going to joescameras.noip.biz. And it's their business to keep the IP addresses up to date. So every time your modem comes back online, it pings the NoIP servers and says, hey, I've moved, I'm here now. And the NoIP guys go, all right, no worries. So any requests that come in for Joe's cameras at noip.biz go to the right IP address as it goes. There are issues with that, obviously. Free services require you to click a link every 30 days to make sure that they know you're still active and you're still using the service. If you pay for the service that's there, that's great. If the service goes down because they're doing maintenance or they've got problems or something else causes it to be blocked, your device can lose sync with it. And if this is a houseboat on the Murray, 500 kilometres away from Melbourne, chances of being able to pick that up easily, reconnect and do all the other things you need to do, it's more complicated than the average person's going to work with. So dynamic DNSing has its own issues there too. So basics on IP address from here. The last thing I want you to look at here is if I wanted to try and translate this to an analogy for everyday use. I tend to think of these things as postcodes, street addresses, building addresses and units, let's say, or floors in a building or offices within a building or something similar to that. So take our office here, we're West Melbourne, so that's 3003, so this might be my West Melbourne part of my address. The next section that's along here might be our street address, 562 Spencer Street. Move along here, this might be my floor number, so floor 1. And then from here, I've got my office number or my desk number or whatever else comes out of it from there. That IP address that's there tells you how to find me in the building. So if you're sending me a letter or you wanted to come up and knock on my door, there I am, there's my location. If I wanted to talk to Bilgan, who's a couple of offices down from me, I don't have to go back to my street address to all the way back to here. I can just talk to him from office to office. And the idea of that, where this last number or the last part changes, is what's called subnetting. And a subnet is something that allows simple access to local devices on a LAN. So if I allow just this last number to change, I've got up to 255 odd addresses, providing I've got no routers and other things that are on there. So within a normal network, that's more than enough. For a domestic home, you might have 40, 10, 100 different devices that are connected to the network, depending on what you're doing. With one subnet, a simple subnet mask, that all works really, really well. And this idea of a subnet mask is something I kind of have to demonstrate or show off to make sense. So what we're looking at here, we've got 4 strings, or 4 different areas. So let's look at doing a subnet mask. You might have seen them written like this before, 255, this is a horrible pen, .255.255.0. So if I look at this as it is there, that's a standard subnet mask for it. What it means is that I ignore the first 3, they all stay the same, but the last one can vary anywhere within that range that I want it to vary. If I convert this to binary, and I won't do the whole thing, but 1, 2, 3, 4, 5, 6, 7, 8, and so on and so on, and then so on and so on, and then we've got 0, 0, 0, 0, 0, 0, 0, 0. And this is where the idea of masking comes in. I've got 1s here, blocking any kind of change for those first 3 numbers. My last one here is a 0, so I can vary that number if I want to. Now, have you ever used a subnet mask that's different than that? Where it's been something other than 255.255.255.0? Probably not likely. Bigger corporate networks will do it. If you're setting up complicated systems, you may need to do it as well. If I alter this number that's here, I alter where my zeros are in this table, and therefore I can alter more numbers of my original address. So if I change this to 254, or, well, 254 is the easiest one. If I do 254, 254 is 1, 2, 3, 4, 5, 6, 7, 0. So now, if my IP address range is 192.168.11x.x, now I can vary that last number as well as this one. So on a domestic network, that might be 1, 2, 3, 4, 5, and so on from there, and I can adjust that last number as well. So this is a subnet mask that will allow you to go from 192.168.1 something to 192.168.0 something, or .2 something, .3 something, and so on. So if you have devices on multiple networks, you can do it this way to make them work. Okay? Something worth playing with your own routers at home, to have a bit of a look at and see how it all works together. But the idea of a mask being something that actually masks the values makes a lot of sense. All right, does that make sense to you guys? Are you happy with that as an idea? Cool. Let's have a look. Go back to this. There we go, our IPv4 stuff. Okay, 3.7 billion public IPv4 addresses. Have we got any left, or are they all run out? Anybody know? It happened a few years ago now that we ran out of IPv4 addresses. There are no more to be assigned. Everybody's bought as many as they can. Telstra's got as many as it can afford, so has every other service provider that's out there, Google and Microsoft and so on, which is where this lot comes along. Now, this is, I guess the simplest way to put this is we didn't have enough addresses, so we created a new way. And so now we have, well, 2 to the power of 128 possible addresses for it, which is that number at the bottom, or 3.4 by 10 to the 38, or 3.4 with 38 zeros after it, or 37 zeros after it. It's a new word I'd never heard of before, but apparently an undecillion is how many that is. 340 undecillion IPv6 addresses. For you guys that come up against it, it's more worth to recognize it. They operate more or less the same way as a traditional IPv4 address is, except there is a lot more to each of this bit. So these 4 that are here is this string of 16 zeros at the end of it. So each one of these represents 4, and they're also hexadecimal as well. So instead of being 0 to 9, you've now got, you've got 0 through to F. So you've got 16 possibilities on each one of these numbers, and hence the gigantic number of things it can do. The cool thing I like about it is if you've got 0 sequences here, you can actually get rid of that part and just do colon, colon. So if you've got a sequence in the middle that's 0 and 0, you can put a colon there, and ignore the bit in the middle of it because the system assumes that it's right. Subnetting works the same way, all that sort of stuff is the same idea, it's just a more complicated version of the same thing. That makes sense? Beautiful. So yes, this will be what we start moving to, but most of it will happen in the back end. You probably won't even see it for yourself. And I think I've duplicated a slide there, but let's go to a reserved IP address. I said there are about 3.7, whatever it was, billion IP addresses, something similar to that before. There are some of these that are reserved. In other words, there's an address range here, 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 and these are designed specifically for certain purposes that don't go out to the outside world. So, most common one you would see is this, 192.168.0.0 to 192.168.255.255. About 65,500 addresses in that, designed for a private network. So, most common networks at home use 192.168. something, .0.1. Here is 168. And the other one that Telstra uses a lot is the 10.0.0.0 range. Not really sure why they do, they just do. So you might see a few of those out on the site. And it's the same sort of idea, you've just got a few more options in that particular range to work with as well. So, let's have a look, jumping on. Dynamic Host Configuration Protocol. And I've called this the wrong thing for years. I've always called this a Dynamic Host Control Protocol, and I'm wrong. So I'm going to have to try and make sure that I get this right. Control makes more sense to me because that's kind of what it does, but configuration also, same idea. So on a router, your network is 192.168. something, and I'm going to let my router assign IP addresses. I am going to let them start from 1.2 because they're already sitting at 1.1, and I'm going to give it all the way up to 1.10. I'm giving it 10 IP addresses that it can play with if it wants to. So when a device connects to my network that has DHCP on it, like my phone, first in, going to get the first IP address that's there. So my phone goes to 1.2, my laptop might go to 1.3, and my tablet might go to 1.4. Make sense? That's how DHCP works. Give it a whole bank of addresses, and then it automatically assigns an IP address to any device that comes on that says, hey, I support DHCP. That's the simplest thing for it. It's how most home networks and routers work because people don't want to configure it, don't want to play with it, they just want it to work. So when you set up your smart TV for the first time, it says, I want to connect to Ben's wireless network. So you put Ben's wireless network in there, you put my password into it, it automatically negotiates and says, hey, you guys, you're a TV, that's fine, you like IP addresses, that's great, here's 192.168.1.5. Simple enough. Now, if my TV drops out, comes back in, it'll probably get 1.5 again, but not necessarily. Might be 1.6 tomorrow, or 1.7, or it could be something else along the line. That's the dynamic part of this. It will vary backwards and forwards. For a phone, a tablet, a laptop, no real problems with any of that stuff. What about if it's your network attached storage? So a series of hard drives attached to your network, which is where you back up your files, your camera, your photos, and whatever else like that. If that changes position every time, I've got to go looking for it with my app to go, oh, my photos are here now, I'm going to have to change that back. So dynamic is good up until a point, but when you want to give something a permanent address, that's where you come up with static and manual routing. So every modem or router has the ability, every router has the ability to do this, and a lot of higher level switches, layer 3s and so on, will also do it. So I've still got the same bank of DHCP IP addresses, so 1.2 through to 1.10, but I've said that my CCTV recorder with this particular MAC address is only allowed to connect at that IP address. And my NAS drive is only allowed to connect at that particular address. So when I go through it, my phone connects, my laptop connects, my tablet connects, my TV connects to there, my fridge connects to there. Those two are going to stay there no matter what happens. If things drop in and out and go backwards and forwards, my CCTV recorder and my NAS drive are going to stay where they are. This is when I've assigned it within that DHCP range where everything else is. But if you remember, my last digit there can vary from 0 to 255, or 1.2 to 255. Within that, I can choose any of those IP addresses to put my stuff. So if I wanted to leave this section free for anything that wants to come along, all my temporary stuff can go backwards and forwards in here, I don't care about. I could put my CCTV recorder at 11, my NAS at 12, my cameras at 20, 21, 22, 23, and so on, and they're not going to affect anything to do with the DHCP. How does that sound? All right, so for static devices like cameras, like CCTV recorders, like NAS drives, some computers, you might get better performance out of your PlayStation 4 or Xbox or something like that if you can static address that as well. We come across it a lot in our hi-fi department here with things like the music cast components on a network. If they're dynamically addressed, every time you go back into your app more or less has to find where they are. And if they've shifted since last time, there's a bit of a lag and a bit of a delay. So for somebody in a store who's just trying to play music or change the track because they hate it or whatever else is going on, if they've got the wrong IP address, there might be seconds taken where swear words are coming out in the store and the 4-year-olds are running around learning new words. That's a problem for somebody. Static addressing those so that they don't move around is a really safe way to do it. Generally speaking, you can do the static addressing in the router. So you choose the MAC address for the device that you want, and that's how the router knows what it is and assigns it to that. You can do it in the phones, tablets, laptops, NAS drives, and the rest. Set it static in their system settings and don't tell the router about it. Now, that works up until a point. And the big problem is, if I've chosen this range and this IP address to put my CCTV recorder, and I didn't tell this thing, then it's going to try and assign that IP address to something else, potentially. And this happens a lot with CCTV. We get questions on this sort of thing all the time. People tick DHCP, get it on the network, it's sitting at 192.168.1.3, power goes out to everything, router comes back up nice and fast, the NVR is just a bit slower than the tablet is or the TV is to reconnect, and now the tablet's on 1.3, and the CCTV recorder goes, great, I'm on 1.4 now, but your app doesn't work, you can't find it via your web browser, you can't do any of those other things because DHCP screwed you. So knowing what you're doing with your IP address, assign manual ones when you can, it makes it a lot more sense.
So how do you assign them again to router?
So router is the best way to do it, and then in your NVR and cameras and things like that, you can assign them after that. I don't know, for people who've got a more complicated or even a simple network for your customers, this is a fair few slides ahead of what I was going to do, but you may want to do a little diagram for them. So this is draw.io, and this is a free bit of web software that allows you to more or less create web diagrams, however, network diagrams and a whole heap of other types of diagram. So for your customer, if you're putting in a CCTV system, you might have your firewall here, your router here, a hardwired link to this, put the IP address for that CCTV system, all your cameras linked with their IP addresses linked off that one from there, wireless devices that are currently on the network, the TV, the NAS, or whatever else like that, full on this list. You can give it as a printout or you keep it for your records so that the next time you go back to site and they say, hey, I've got NBN and all my IP addresses have changed, you can go back in there and go, all right, well, the CCTV record was here, need to log into that, need to reassign, cameras were here, need to log in and reassign, and so on for it. It's a really quick and easy way of doing it, and it is totally free. You just have to work with whatever diagrams and things they have. That's a pretty simple one, and that's one based on Cisco images. So from here, we've got our internet connection, we've got routers, external servers connected, different access points and switches and everything else like that from a network. You can make this whatever you want it to be. Really, really cool service. It's from, I think, the guys that do AutoCAD, if I remember rightly. And you can save them, you can do, swimming lane diagrams, map layouts for buildings and all sorts of other stuff as well. So there's a lot of unusual types of things you can build, including circuit diagrams if you really want to do one of those as well. But yeah, draw.io is a really, really cool service, so it's definitely worth looking into. All right, so static manual routing and DHCP, does that make sense, what we've talked about there? IPv6 versus IPv4, same idea. Nothing changes there except the numbers do.
So you turn off DHCP if you haven't tried.
Yeah. Yeah. And you're not normally going to turn it off in the router completely, because the router won't do anything then, and every device will get confused. But choosing a range of, say, 100 DHCP addresses for an average network at home is huge. So 192.168.1.100 through to 1.200, let's say. Got 101 addresses in there that you can assign all your devices to. And then below that, you can throw your NAS, your fridge, your whatever else you want to make static underneath that, and off you go from there.
Sorry, Ben, so you can have both then?
Yeah, absolutely, yeah. And there's nothing stopping you from assigning an IP address that doesn't work with your network as well. So if I wanted to call one of my devices, let's say my recorder, I called this 192.168.2.1. I haven't got the right masking in place, I haven't got anything else like that in there. The thing still exists, it's still connected, the cable might light up and all the stuff like that might still happen, but I can't see it from my modem. I can't see it from my router because the router doesn't know it exists. All these other things aren't going to happen for it. And that's because of that subnet mask that's set up. The subnet says to the router, only look for and use devices within this particular range, okay? That makes sense? Those of you who've set up wireless links before, point-to-point links, I'm going to do that a bit more on that in a second, but a wireless link like that one, you're normally going to chuck that in a subnet range that's outside the range of all your other devices as well, because you don't want people messing with it. You just want this thing to sit up there and do whatever it does forever and ever and ever. If you want to actually connect to it though, you can't do it via your modem. You can't plug into your normal switch the way you typically would. Instead, you have to do something a bit special. Again, I'm jumping a different place in what I was going to do, but if I wanted to, I can assign myself a manual IP address for my computer to log straight into a device. Okay, so let's say I'm setting up a modulator, like one of the Zycast modulators. By default, DHCP is switched off because they assume that when you're putting it into a network, you want it to be somewhere specific. It isn't going to be jumping around and playing around with everything else that's going on. So from this, I need to be able to go into my settings and be able to say to it, well, I need you to be on a specific IP address so that it works. So in Windows 10, I've got the option here of going into my settings for here, and I can go manual IP address for IPv4. I can set it to whatever I want it to be so that I can talk to my devices, and so on and so on. 255. So they call it prefix length, which is weird, but anyway. 0. Sorry, yes, on the wrong. Let's do it the other way. Apologies for that. Let's do this way. And you're going to make me do this way, aren't you? Yeah. Let's flip this across to the other screen. So from our basic network settings, or our general settings for it, my Wi-Fi that's here, I've got the ability to play around with my options. So I can go to change my adapter options from here. I've got a little window that opens up on the other screen because of course it does, just to irritate things. I've got Windows adapters that I haven't got connected in for Ethernet, and I've got my Wi-Fi that's here. From this one, I can view the status of this connection. If I do this, again, it's coming up on the other screen, because why not? I can see that I'm connected to this particular network. I can see the SSID of the wireless network, how long it's been there, and everything else. I can also, let's see if this does its thing. Yes, it does. There's my MAC address for my wireless card that's in the computer. There's my IP address that I've been assigned to by DHCP, and so on. That all works pretty easily. And there's my IPv6 one that's assigned. I've got my DHCP server and gateways and all that sort of stuff in the system as well. For an average home, gateway and DHCP server are probably the same thing. Some that won't be. My wireless properties, I can do a bit of playing around with all of these things if I want to, or I can go into my properties, I can go to my protocol version here, go to here, and I'm on automatic, so this is my DHCP settings. But if I want to connect to a device that's on 192.168.2.1, I need to be on the same network and same subnet. So I would choose this to be 192.168.2. say 10. I'm going to use that subnet mask, my gateway 168.2.1 or whatever is appropriate for the other devices that I'm using. Use that one in there, and I can use my DNS servers of the same ones that I like that I've put in before. And when I do this, now my laptop won't talk to the Radio Parts Wi-Fi anymore. It'll only talk to any device that's within the 192.168.2. something subnet. Does that make sense? So if you're setting up a camera system for the first time and it's 192.168.1. something, your home network might be on 10.0.0. So you can play around with those IP addresses. You can set these things manually on your laptop, so you can get in, do the setup, change the setup for the network, get it online, and then you can do all the rest of it the same way that you did before. That particular way of changing your IP address manually works on a device like this one where I've got Wi-Fi and Ethernet options. I can have a manually fixed IP address for my Ethernet, and I can have a Wi-Fi one onto the rest of the network for DHCP on the other one. And I can talk from one to the other and set one thing up and do the other thing at the same time. If you have external Ethernet connectors and things like that, you can do the same sort of idea as well. That one is very, very useful when you're setting up a lot of different systems. So, all right, static and manual routing. Port forwarding. This is another part of the same sort of idea. A port is basically a hole in your network that traffic can pass through, or packets or frames or whatever else, depending on what you're trying to do. So this computer here has requested a web page. It's requested it through the router, out through the internet, and this is the actual server that's providing it. This server sees the request coming from this router because this router is the only IP address that the rest of the world sees. Doesn't see this, doesn't see that, doesn't see any internal IP address, it only sees the external one. So, as far as it's concerned, this device, 14.15.16.100, my router has asked for a web address. It's also asked for a secure website, a HTTPS website, all through here and out, but that's a different service. At the other end, it sends this information back via that port to here. The port forwarding is set up in here so that only 443 traffic goes this way and 80 traffic goes this way. When you've got a CCTV system, there's a service called Universal Plug and Play that most of these systems use. The idea behind it is, I switch it on in here, I plug it into my router, and the NVR says to the router, hey, do you support UPnP? And the router says either yes, I do, or no, I don't. If it says yes, then the router says, the NVR says, great, I need these ports open for me, and any requests that come in on these ports, send them to me. And the router says, your MAC address is this, these ports are now going to come to you. Simple as that. So if I'm watching a camera remotely, I'm going to use probably 3 or 4 ports to do it. Might be a video port, might be a framing port, there might be a control, a PTZ port, and there might be a web port or some other feed that's coming along for it as well. I don't need to know what any of those things are because UPnP's done all of that automatically for me. So UPnP's great, right? Always works, right? We don't ever get phone calls about that one, right? UPnP is a bit the same as anything else that has universal in the name. It's not always universal and it doesn't always work straight off the bat. The simplest way to fault find it is to turn it off in both devices, turn it back on in both devices and let them re-find each other and do their thing. If you've been mucking around with IP addresses for your device, it might still have your old UPnP settings for that MAC address in there, and so it's now lost it and it's trying to send the traffic the wrong way from where it was before. Turning it off, turning it back on again, it's the old IT trick, works a lot of the time. That's the basic idea behind port forwarding. There are other things that you could use this for, so games that use particular voice services or VoIP phones that need to dial in or out. There might be a VPN that you're using that uses a particular port to send information backwards and forwards. Keep in mind that every time a port is opened through your router, that is a potential vector for somebody to get into, infect it, hack into it, or do something else like that. There are particular things like SSH and Telnet and so on where if you give people full access to it, or they can have a field day with your internal network. So knowing what is open and what isn't open is a really important thing to do. It also brings me to one of the other programs and apps that I like to show off to people. So this is a little program called, well, it's actually called Nmap, which is based on a Linux command system and the rest of it. What this does is it searches via host to find out what services are running, including ports that are open and everything else like that. So I did a search on our Wi-Fi network here, and I looked specifically at this particular product, 192.168.168.160. Now, all I did was do an intent scan. There are a few different options on it as well to try and do its thing. So it goes through, it has a look at everything that this particular thing can do, and it's got a whole heap of ports that are open for it. You've got a whole heap of different services that are available for it as well. And if we get down a little bit further, we find out it's a LaserJet printer. So a LaserJet printer, for some reason, needs HTTPS 443 port and a web port and a whole heap of other stuff like that as well. Not quite sure why a printer needs all of that, but it does. And yes, you can find out a lot of information, obviously, from this deep scan. In a more simple sense, you might just be able to find out what ports are open from this device that's there. So Nmap, and they call it ZenMap here, but that's the graphical user version of Nmap. So it makes it a bit easier to understand than a whole heap of strings and information that comes out. So yeah, cool little program, and it's free as well. So if you ever want to try and work out what's going on in your network for devices, this is a good one to do. Speaking of all of this, there is one other little service while I'm talking about them that you should all know about, and that is CMD. How many of you have used the command prompt for in Windows 10 or Windows 8 or 7, all the way back to DOS 3.1 or 2 or earlier and earlier programs of it? Cool. All right, so if I show you the most common one that I use, there's my horrible thing. Go to Start, type in CMD, there's my command prompt, and there we are. Wow, DOS inside Windows. Not really, but almost. From this, if I type in ipconfig, I get this little list that comes up, and it shows me my different network connectors. It shows me which one I'm actually connected to, shows me IPv6, my IPv4 address, and so on for it. That for me is a hell of a lot quicker than jumping into settings on Windows, going to Wi-Fi settings, finding the right adapter that's active, going in, looking at the properties, and looking at the connection that's there. I've done like 50 different clicks to get to that point. I can type in CMD, enter, ipconfig, enter, and instantly I've got my gateway address or my router address, my subnet mask that it's using, and my IPv4 address straight away. So if you're on an unknown network, you plug in, connects up, Ethernet's there, everything's running. That's a really simple way of finding out exactly what's going on with your network. There is one other way that is a little quicker than the standard. There's my Wi-Fi. Click on Properties, scroll down the bottom, and there's my IPv4 address and DNS servers. This doesn't show me my gateway, so I would have to guess. And in this case, if I guessed it was the same as my DNS server, I would be wrong. So it doesn't quite give you the same information as doing the other one does. Yeah, and I can copy that and MAC address and all the other bits and pieces from there. Cool. All right, so that's, yeah, fantastic little thing that's been in Windows for goodness knows how many years now. And there are so many things you can do with a command prompt that are so easier to do that way than they are to do the others. Okay, port forwarding roughly done. Wi-Fi, moving on to basic terminology for Wi-Fi. It does not stand for wireless fidelity. Wi-Fi was actually made up. It was a marketing company or an IT marketing business company that was tasked to come up with a more attractive name than 802.11 for the IEEE standard. So they came up with Wi-Fi. There are two different main bands that we use now, 5 gigahertz and 2.4. 5 gig can get more bandwidth, get more speed, but less range. Doesn't penetrate walls as well as 2.4 does. 2.4, less speed, but it goes further. Simple as that. Usable range from domestic stuff and routers, I don't know, 30 to 50 meters for a phone or tablet and small things like that. Use a proper access point, use something more serious, you can get 70, 90 meters or more, but I generally wouldn't push it too much further. There's a very simple reason for that. The antenna that's in this doesn't have to be particularly strong to pick up a big, heavy Wi-Fi signal. But unless the antennas way back 70, 90 meters, however far away, are really good and sensitive, they're not going to pick up the signal that this puny little antenna is trying to send back to it 70, 90 meters away. In an average domestic house, I would probably be putting wireless access points, one per floor, or maybe one per 30 to 50 meter worth of radius. With an LR like this one, they're actually quite sensitive, so this thing can push all the way out to 90 meters. But again, if you've got the cheapest phone, the cheapest tablet, the Fisher-Price tablet first for your kids, the Wi-Fi adapter that's in it and the antenna might not be very good. So keep that in mind when you're putting this stuff together. A few different things on generations of Wi-Fi. The most important thing is they've started to call generations now. So Wi-Fi 4 was your N generation, Wi-Fi 5 was AC, where we started adding the 5 gig stuff into it, and AX is the new version of Wi-Fi 6. I've got one Wi-Fi 6 device here, that is TP-Link's AX. If you look at the TP-Link's range and see anything with AX in the name, it's a new Wi-Fi 6 802.11 AX based system. Same frequencies as before, but a lot of cool technology in the back end to make the signal go further, be better, faster, and all those other things like that. You can obviously see that you've got some serious jumps up in terms of overall speed and link rates for it. Keep in mind, Wi-Fi gets attenuated by water, and you are meat bags full of water, so you standing between your wireless access point and the phone might be enough to make it drop out. If you've got a pool and it's in ground and you're on the other side of it, then that might cause you issues as well. And Wi-Fi does not penetrate metal shed walls. So if you want Wi-Fi in your shed, you're going to have to find a better way to do it. 2.4 gig has only 13 channels available in Australia, but when you look at the way that these channels spread, you need a bit of space between them to make them work. So here in Australia, we only have 3 channels that don't overlap. That's channels 1, 6, and 11. In your home, in your business and everything else like that, you should only be using those 3 channels. That's one I found online, and that is in Hong Kong in an apartment building, and it's basically Wi-Fi hell. There's people who are not just using a single 20 meg band, they're trying to use a 40 meg one instead to try and get more signal down. There's so many different people at these main ones that I imagine your Wi-Fi is going to really suck badly here. If you've got a site where you're putting in wireless access points and they're all 2.4 gig ones, be very clever about how you do it. So if I've got one in the showroom here, one out the back in dispatch, and one over there in the showroom, I might put channel 1 here, channel 6 there, and channel 11 over there. My next one in the showroom, I might put back on channel 1 again. The next one over that corner, I can't put to 6 because 6 was here, so I'm going to put it 11. Then the one that's directly above, I'm going to, and so on and so on. So stacking that out and laying it out makes a lot of sense. Good systems will do that automatically for you, but if you think about it logically, that will help the system along. 5 gig's got a lot more space, a lot more channels, so they work out really, really well. I'm going to get back to this towards the end so I can keep skipping through. Wi-Fi problems, there are so many of them, but I'll get through a few little basic ideas. There is a free bit of software for Windows 10 called Wi-Fi Analyzer. If you've got an Android phone, there is also Wi-Fi Analyzer for your phone, and it does the same sort of job. You can do a scan and find all the wireless networks. There are 2.4s and everything else like that for it. This is actually the one I did upstairs yesterday. And you can see these rogue ones that are here are from the backpackers across the road. So they don't know about good Wi-Fi and how to set it up properly, but you know, there it is. You can see there's one on number 7 as well, which I think is one of our customers who lives across the road from us here. I think he's done something a little bit rogue with his as well to try and get a bit of extra bandwidth, but anyway. And that's the 5 gig network by comparison. Here upstairs, there's almost no channels being used, and I've got all that lovely space in the middle. So 5 gig's fantastic if I can make it work. From the software, it'll also give you, so our RPG device network, 1, 2, 3, 4 different wireless access points. They're all unique in terms of their MAC addresses or BSS IDs in their case, but they're all linked together on the same network. And you can see these are all the 5 gig versions of it, and there are different frequencies depending on which particular station they are, and they're all talking together to make sure they don't cause problems. They've got security on them. Our guest network has no security at the moment. Kind of does, but that's a different story. Yeah, so easy enough to work with, and it's a simple program to give you an idea of what's going on site. Again, free. All right, point-to-point and point-to-multi-point links. Excuse me. All right. So the simplest way to put this is cables without the cables, or a virtual cable. I set up 2 devices, say 2 of these. This one I set up as my access point, and this one as my client. This one I give a network name like, I don't know, ShedLink, for example. And this one I connect to ShedLink with the password, and I put nothing else on the same network, subnet, or anything as these 2 devices. So I can't connect to it on my phone, I can't connect to it on my laptop while I'm out in the backyard. All of my bandwidth is being used to stream between these 2 points. And so in my shed, where this one sits, I've got it plugged into an Ethernet switch or into a wireless access point system down there. So now I've got wireless in my shed, but not because of the link, but because the link works as this virtual cable. Easiest thing to do, we sell a heap of these, and there are different ways of doing it. So that's an old system now that one of my customers gave me to play around with. There are light beams like this one. This one's actually got a 120-degree spread on it, so it'll pick up even if your angle is a little bit off from where you want it to be. The Nano, which I think is this one at the back, this is a narrower thing. We call this a Mentos on a stalk. Put this up onto your mast, onto a standard antenna mast, get the angle right, put another one at the other end, get the angle right for it, and create a 5 gig link between the 2 of these things. Can't remember the maximum range on these things, but it's normally like 10, 13 kilometers or more if you've got line of sight. So keep that in mind. If you're doing a nice big link, get it that way. I was involved in a link a few years ago, quite a few years ago now, in California, that ends up being a multi-hop, multi-stage link that ends up 180 miles from one end to the other. And they were wireless links all the way along to make this thing work from valley to hill to valley to whatever else like that along the way. So you can make these Wi-Fi networks absolutely massive if you need to. And there are different options depending on the distances you want to go and everything else. There is a really cool article on the Ubiquiti website, which basically says to you exactly which products you should use. So, this range, this frequency, this speed, this sort of application, and off you go from there. A point to multi-point is the same idea, but more complicated. My source, which might be one of these, so I've got a 120-degree spread. I put this up on my house. Then I've got a factory building over there, I've got a shed over there, and I've got my workshop over this side, all within that 120-degree arc. At the other end, I put up, say, the 5 gig version of these things, put one of these on each of them. They link back to the single central point. And this one allows it to send and receive information from all of those stations simultaneously. There are bigger, more powerful ones that do a full 360-degree omnidirectional signal. There are ones that will do 100 kilometers worth of line of sight. There are microwave links that work the same sort of way. WISPs and ISPs in remote areas use it, all that sort of stuff. So heaps of those options out there for it. Point to multi-point is great for established architecture. So campuses, buildings like sheds and farms and so on. If you're going to have devices where people are roaming out into the yard and they want to be on Wi-Fi, if you've got people in the paddock and they want to be on Wi-Fi, that's not what this is for. This is to create a virtual cable network instead. Does that make sense? Cool. Easy. Right, so concepts are done. And it only took 40-something minutes to get that right. Components and the hardware parts, I'm going to go through quickly. Modems versus routers. Any of you with NBN these days will know that most NBNs supply the modem, but not a router. You have to get that separately from your ISP or bring your own one or whatever else it is. In my house, we had really, really poor ADSL, so I had an ADSL modem router that I turned off the router part because it was crap. Put in my own router on the other side of it, all my devices were connected to that. When NBN came in, all I did was rip out the old ADSL connection, put the NBN cable modem in, set it up, and now my router stayed the same. All my devices considered the same thing, but now I've got 50 times the speed that I had before. So Ben is a very happy man when that happens. That's the way that a modem and router works. The modem only translates the physical hardware coming in from the street to something that works internally for you. And then your router does all the rest of the connection and all the rest of the talking. So routers will assign IP addresses via DHCP or manually. They'll firewall traffic from getting into your network. They can DMZ it and a whole heap of other things as well. They don't access the internet directly. Okay, so a router's not going online for its own reason. It still needs to go through a modem of some kind to make that work. Okay, just to change from one format to another. And there are a heap of different options for it. One of my favorites is actually this little thing, this Edge Router X. It is one of the most powerful little devices you can buy in terms of home network routing, particularly for gaming. It can do some stuff with quality of service and I can't remember, they've got their own specific term for it, but a better version of that that allows your latency to drop way, way down. So really cool little devices. But this is just a router and it's got a few little ports on the back of it for a couple of local devices. There are bigger versions of these that have PoE ports as well. There are ones that have fiber ports and other things. All of them are pretty cheap, reasonably easy to configure, although less so than, say, the security gateway, which is Ubiquiti's sort of all-in-one software version of the same idea. But the Edge router's got more brain power, much, much more switching capability, better routing, better quality of service, etc. stuff on it. Configuration, if you can get it right, will do a really, really good job for you. Then add your wireless access points onto that to get your all-encompassing Wi-Fi system. Okay, moving on. Wireless access points. Most of the guys from here have sold them. Most of the installers have installed them and used them. There are a huge range of them. Ubiquity's LR is there. We've got, that's a TP-Link, which one? EAP 225, there's 245s. That you can use as a wireless link. That you could, but you wouldn't. And there's a few others that I haven't brought down as well for me. All of these have different capabilities based on what you're trying to do, but the basic idea for them is they're a Wi-Fi hotspot. All they do is act like a wireless switch. Multiple devices to one hardwired connection back to the rest of the network. So, cool ones of note, TP-Link's little outdoor units, a little mesh one. This is the new UAP-AC Nano. They're the small size of the Lite, but they've got better antennas, more stuff, more expensive, and you can buy optional skins to put on them. So there's a camo one, there's a marble one, there's a concrete one, a black skin, there's a few others as well, so that you can really customize it to your customer's house, more or less. Where style makes a difference, there are options there for it. This is how you distribute Wi-Fi properly. Mesh networking is a version of the same idea, except every single point in a good mesh device, and I consider the Deco as a good one, every single point that's in here is both a router, a switch, and it can be wireless or hardwired back to the main system. So if I've got this showroom and I can't get wires over there, I can plug it in there and create a wireless link to this one where I can. And it doesn't matter which device is which one, they're all absolutely interchangeable at any point along the system. A lot of other systems, including the amplifier one that these guys do, including the entry-level TP-Link one, and a lot of other brands will have a master unit and then a whole heap of mesh units that sit on the outside of that. If something happens to your master unit, the rest of it goes down and dies. If something happens to one of the components on this one, the rest of it's still up and going and keeps working for you. TP-Link and all the mesh suppliers for that matter make their setup really easy. They give you an app to do it, register it, set it all up, give it wireless names and security, turn the Wi-Fi off for the kids at 9 o'clock at night, do things like virus software built into the Wi-Fi itself. All that very, very cool stuff. So mesh is a great solution for a home. Business, if it's small enough, might be okay. For everything else, probably not. I like the fact you can create guest networks really easily with it as well. So one of Darren's customers over in South Australia put 3 of these, I think, on a caravan park. This is Ubiquity's powerful outdoor mesh units, all linked wirelessly except the main one, and you're covering, what was it, it was 600 meters by 400 meters, I think. The whole site has been covered by 3 of these. And if they added more space next door, or if they wanted to cover the beach that's just down the road, they could add another one of these things in just by putting power to it and then putting it up on a pole and off you go. They can create multiple network SSIDs, so wireless network names. So you can have a guest network, a staff network, a device network, and all that other stuff all within the same devices themselves. Simple configuration, all that sort of stuff works really, really well. So wireless access points and mesh, different things. Switches, yes, you've seen these before. Multiple Ethernet devices to a wired network, simple. Some routers have got it built in, some don't. There are different standards that are based on the number of ports, the speed, processing power, the layers, and any sort of physical considerations. So I've got a couple of rack-mounted ones at the front that are there. There are some smaller ones. That one's a PoE switch that's there. There's another one sitting up on the top here as well. Choose the ones that match with what you're trying to do. Optical ports or not, etc., etc. Okay, layers, because layers are complicated. Layer 1 are physical layer devices. In other words, they're dumb. So think like there is no particular brain power switching or anything else that's happening in one of those devices. If you plug 5 devices in and they all start broadcasting at the same time, every other one of those devices is going to get whatever they send out or whatever they receive, all at the same time. So if I've got a printer connected to a basic little switch like one of these Cisco's, got a printer connected to one port and I sent a print job from my computer, all the other devices that are on there will also see that print job. Not good for security, but on a small domestic network, it doesn't really matter. So they're often called hubs when they're dumb, but a basic switch, very, very simple to do. Very inefficient, but for homes and things like that, they're more than enough. Until you start adding 10 CCTV cameras to a network and you start pushing more and more and more traffic into it. There's some really basic switches from Edimax that do what's called a port. 5 ports that are on it. One of those ports acts as the master link out to everything else, and all the other 4 ports only talk to that link, they don't talk to each other. It's more or less blocking the traffic from going the other way. If you're an electronics person, think of it like diodes. You know, voltage will only go one way. Layer 2 switches and layer 3. The layer 3 switch is more or less a router. A router might be able to do the same, or generally does the same things and more so, but a layer 3 switch, depending on which one you choose, can do all the same sort of things. The most simple way I can think of to do it is to say a layer 2 switch does everything via MAC addresses. So it has a web interface and you go in there and it looks for all the devices. And so if I always have a printer with MAC address X sitting on port number 73 or number 6 on this particular one, any print request I come in that says I'm for MAC address X will get sent to that port and only that port. That sort of network is great for homes, it's great for small businesses and so on, where you've got a reasonable number of devices. This, in its memory, keeps a list of MAC address equals that physical port, MAC address equals that physical port, and whatever else it goes through. WebSmart, EasySmart, Smart, and all sorts of other names are pretty common for layer 2 switches. You'll often not find them called a layer 2 switch because it might have some or all or none of the features, but it's still a WebSmart or an Easy, and whatever. It's complicated. Basically, the more money you spend, the more smart you get. The last ones here are layer 3 switches. You guys probably won't come across them all that often with domestic jobs, but if you put a Bluestream video over IP system in, you need a layer 3 switch. Simple as that. You're passing gigabit, standard of traffic and packets everywhere you go throughout the network. You're broadcasting one device to many devices or many devices to many devices all through the network simultaneously. You need some hardware and software in the back end that knows what it's doing to be able to pass that information properly. Generally speaking, layer 3 is where you start looking at VLANs. And a VLAN is more complicated than I really want to go through today, but the idea is if I've got those 192.168.1 addresses for my stuff, my cameras, say my camera system's all on .1 something, then I could put all the rest of my hardware on .2 something. All my cameras and NVR talk to each other, everything works fine, but only the NVR has passage through the VLAN, through the switch, to my other network so that I can view those cameras via my PC or something similar. Even though they're all on the same switch, those ports don't see the rest of the switch, and these ports don't see the rest of them as well. It's great in big traffic systems where you need to identify and get it where it needs to go. In a technical sense, these use MAC addresses. These use MAC addresses or IP addresses, depending on what you're trying to do. Within the same subnet, MAC addressing. Outside of that subnet to another VLAN, then you're going to use IP addresses to translate from one to the other. That's a short version of VLANs for you, and probably more than we want to do today. Last little thing here, in terms of hardware, is a router, switch, and access point, which is what most people buy. This is one of those. It has 4 ports on the back of it. It has router abilities. It has wireless access points built into it. So this does all the jobs that you're going to need for a domestic house, right? Well, if you're too far away from this thing, or you've got to put it where the NBN connection is in the shed or in the garage or in the wrong spot, this thing might not get wireless where you need to go. What if I need 10 Ethernet ports? Now I've got to add more stuff onto this thing to make it work. I prefer a network where you can build it up yourself. You take a router of your choosing, like one of these, put it into a switch that's got as many PoE ports or basic ports as you like, put wireless access points 1 or 2 or 3 or 20 around the place to cover the whole place and do it properly for you. Then when it's configured this way, all of the parts themselves have got more brain power, more switching capability, more specialized stuff than this does to be able to make your network as solid and reliable as possible. The average customer in the average house, one of these will do the job. But most of you deal with the unusual houses and the unaverage customers, as it were. So knowing the difference and when to jump from one to the next one is important as well. That thing is a new TP-Link one that's got more antennas than is probably good for it. If I brought that home, my wife would kill me, and it still wouldn't get from where my modem router needs to live to the backyard. So keep that in mind when you're working on these sort of systems for it. And they're also a single point of failure. If the wireless goes out on this, then everything dies. The router goes out, the power supply to this goes out, everything fails. A lot of these other ones, like the like the Ubiquities and so on, will have multiple backup power solutions. So PoE power plus 12 volts, or this plus that, so that if something goes down, the system keeps on running for you. All right. So remember, router doesn't equal modem, doesn't equal Wi-Fi, doesn't equal switch. Router is just one of those little devices like that, except sometimes they do have switches, and sometimes they have wireless access points, and sometimes they have all the rest of the stuff as well. Last little bit, and I've done some of these already for you or talked to you about them. cmd.exe, manual IP addressing. Advanced IP scanners, one I haven't shown you yet. This is another program I use a lot when I'm on a network that I don't know. So if I bring this thing up. So I did a scan from this IP address range. This is our network here, 192.168.168. something. And I varied it just between 1 and 254 at the end. And I can do all sorts of other things with this. I can only search for one port, I can search for multiples, I can search specific subnet ranges and so on. From this, I run my scan, it takes a couple of minutes, and then it goes through and finds all devices that are connected to my network. So if I look down, I can find that printer that I was looking at before, which was that one. From here, I can also see that it has a web interface of some kind associated with it. And it will show me there how all that goes together. So if I've got configuration that I need to do, I can do that from there. Go back up a bit further and I might see, let's see here. Where is my... Well, there's a lot of Raspberry Pis. There's the HEOS Home Cinema. So from this, double click on it and, oh no, its web interface doesn't like me. Oh, that's fine. But a MusicCast device might let me log into it to do some of the settings in the back end of it to make it work. Again, if I'm not sure where my NVR is on a network or a camera or something like that, I can use this to scan the entire network in a couple of minutes and find everything that's connected to it properly. I can save these searches when I go back to site. You can see when things have changed and all that sort of stuff as well. It's really mostly just useful for that, to see what's on a local network. Okay. Last one's here. Your browser is one of the most powerful tools you have. You should know that. Wireshark, most of you have probably never used, but this is a brutal network analyzer. This will do so many different things. So this is live traffic on my network now at the packet level. So I can, from here, go into one of these, go into this particular one and find out exactly what the data is, what the string is, where it's coming from, where it's going to, the MAC addressing and everything else like that for it. So if I've got a problem with something on my network, I can dial right down to it and see that, oh, it's talking to the wrong device, or it's flooding the network with so much crap, something must be going wrong here. Wireshark is really, really good for this stuff. Network admins and sysadmins use it a bit. I'm not going to save. From there, a Wi-Fi analyzer I talked about before. Ekahau Heat Mapper, I've actually logged onto this computer, but the idea with that is you create a map of your building or your room, put your wireless access point in there for a test case, for example, and then walk around. So walk from room to room, from building to building, whatever else it is, and you measure the level of the signal wherever you are. And on your map, you basically just click and show on the map where you are when you took that measurement, okay? So it's like, I take one step this way, click the thing, take one step this way, click the thing, or walk to doorway to doorway, from bathroom to bathroom, whatever it is. And you'll find out how well your LR, a single one of these, will do in a house. So set this thing up as a test thing, plug it into power, connect it on your laptop, wander around the house, wander out in the backyard and the rest, build up this map, and then you can show to your customers and look, for 180 bucks, I can cover the house. If you want me to cover the backyard, this won't do it. We're going to have to put another one in here to make it do it this way. And you can show them that without buying expensive tools. It's a free bit of software. It's really, really cool. These three, and you know about Draw.io already, these three are all apps that Ubiquiti makes. And these are setup configuration apps for basic unified network stuff. So if I take one of these access points home, plug it into its PoE injector, plug it into the LAN for the rest of the network. I don't have to put it up in the ceiling. I just put it on next to the modem for now. Scan the QR code that's on the box with the app. It'll locate this device. I then go into my app on my phone and say, I'm going to call this Ben's Wi-Fi 2. I give it a password in there. It uploads the configuration to this thing, and you're done. There's no stuffing around on your laptop with the configuration tools and the controller software or anything else like that. For a simple system where you're only putting a couple of these things in, it's perfect. Really, really easy way to do it. You can set one of these things up in about 4 minutes, and that includes the thing rebooting itself when you do it. Lastly, on that side of things, if you do go more into it and have a bigger site, having a cloud key is a way of running a hardware controller on the network that keeps an eye on what's going on. It logs over time what happens with each different device that connects, how much data they're using, how well the switch is performing, the wireless access points dropping out, and everything else like that, all onto a stick. That's the old version, that's the newer version. There is a version of this that takes a hard drive, so you can use cameras with it as well, and it just sits on your network doing its thing. Or, if you're like me, grab a Raspberry Pi and run the controller software on the Raspberry Pi for $50, and you can sort of create your own version of that one for a cheap price. But that's because I'm tight as a duck's bum. So yeah, that works out for me. Okay. I've kind of ripped through a lot of that stuff pretty quickly. The last thing I'm going to ask you is about your wireless network problems. Okay? We've talked about all the rest of this as a hardware-based thing, but in terms of the issues that you have at home or on customers' sites and the rest of it, are there any that you would like to bring up or ask about or check in with to say, hang on, what's going on here? Why doesn't this work? Anything that sort of springs to mind or weird and wonderful stuff? I guess then the simplest way I would... Yeah, Tim?
Well, I was going to say, in an apartment building, and it's so many different Wi-Fi networks
Absolutely.
going around.
Yeah.
In terms of making that a bit smoother, is that just finding
You're-
a channel that's going to be cool?
You're in one of these, basically. So Tim's question, for anybody who didn't have the microphone or wasn't in the same room, was basically he lives in an apartment building, not in Hong Kong, here in Melbourne, but it's the same idea. Every man and his dog's dog has a wireless access point or a Wi-Fi modem that's in there. In an apartment building where there's 20 apartments on a floor, each individual apartment's probably got their own version of it. So what do you do when your network map looks like that one? The short answer is 5 gig if you can, within an apartment, within a closed space. The 5 gig won't go through the concrete walls very well to next door, so it'll self-contain for you. But you might find that even the 5 gig network is completely saturated, or you have concrete internal walls and you can't go from the kitchen to the living room without the Wi-Fi dropping out as well. The unfortunate part about it is then you have to go for more wireless access points. You're more or less putting one in every single room that you want Wi-Fi. You might dial down the power to them so they're not as broadcasty, they're just localized for you. And when you walk from room to room, from room to room, you're logging into or connecting from one to the next one and so on as you go. In these sort of environments, it's about the only way you're going to get any kind of result to do it. If you could convince everybody else in the apartment building, then you can do other things with it. There are reasons why apartment buildings actually have distributed Wi-Fi systems through them now to manage this stuff and stop it from happening. And then they just charge you by the amount of data that you actually pull down. China in particular, very common, highly built up places like New York, they're very, very common as well. So Tim, if you might want to sell an entire Wi-Fi system to your building, and in which case we've got plenty of products on hand for you to be able to do that, so no problem at all there. Yeah, manager might not be able to pay for it, but yes. Okay, so in that sort of environment, 5 gig if you can, limited range, drop the power down so you can just do room by room, but you might need 4 wireless access points like that in an apartment that's 10 squares because it's the only way you're going to get signal reliably for you. There are other connection types like Bluetooth, there are low energy, there's LoRa and a whole heap of other things as well that might not be affected the same way. Bluetooth generally is, but they might get another option as well. Cool. All right. Yeah, Darren.
My amp goes missing on the network.
Mm-hmm.
Should I then using a static?
I probably would. So Darren's amp goes missing on his network, so he can't control it or use it or do something else like that for it. Most common thing that happens with it is it's dropping out. If it's on Wi-Fi, that's pretty common. If it's on Ethernet though, what's more likely happening is the DHCP is reassigning it as the unit powers down, powers up. There's a thing called network standby, which if it's turned off, it means you can't hit on in the app and turn your device on. It turns off its network card and everything while the power's off. So leaving network standby on uses about a half a watt worth of power to do it that way. Putting a static IP address in the receiver, a static IP address assigned in the DHCP table, or set it outside the DHCP table for the rest, and the amp should always be there when you want to go to it. I've got a few MusicCast wireless speakers around my house. Every single one of them's got a static IP address on the network for it, so that when I go back into the app or when I swipe down from AirPlay, I can always find them where they were last time. So, yeah, works out pretty well. Cool.
Hey,
Or-
Ben, when you were
Yeah, Mikey.
referring to VLAN prior, was that in a sense to isolating from a network as well? So if you were doing, your example was, AV over IP for Bluestream.
Yep.
That's if you were working with 4K stuff, because they do. It's 18 gigabits. So when you are isolating that from a network, are you creating a VLAN for that,
Well,
or subnetting for those particular devices?
so the Bluestream example, you're saying 4K and 18 gig. Unfortunately, they don't do 18 gig. They do 4K 30 and they compress the hell out of it and then uncompress it at the other end. So it's actually,
10.2 gig?
it's only down to 1 gig. Like the packets and the transmission's about 1 gigabit. So give you one little side note on that one. If I had some of my devices on here and then I linked across to another one of these in another part of the building, and I only had one gig cable running between these two, I'd only be able to send one stream of video from one of these switches to the other one. I had a customer not that long ago who had all of his gear in a rack at this end. It was all beautifully set up and laid out and all into a nice PoE switch. And they had a single Cat6 running across the other side of the building, and then they had 37 receivers on the other side of the building. And they wondered why they couldn't ever stream more than one of the transmitters across the receivers. And as soon as you start looking at the bandwidth, one Cat6 cable is nowhere near enough to be able to carry 3, 5, 10, 50 different transmitters across the link. So they had to do something a bit smarter to actually get that working and run some more locally and do other things like that as well. Okay, so that being said, they're running at about 1 gig. That traffic's being passed backwards and forwards, and it's doing a thing called multicasting. So if I put in one transmitter, I could do 2, 3, 5, 10, a video wall of 12, 3 by 4 or something like that running through it. That uses up a lot of bandwidth, a lot of data. If I put that on the same network that my VoIP phone system is, if I put it on the same thing as my streaming video for my gaming channel might be, then suddenly all of that traffic's getting knocked to hell because of all the video streaming traffic from the Bluestream stuff. So they have particular hardware that helps do this, the controllers that they sell. So the ACM 200s and the ACM 100s do, or CM 100s do that. But really what you're doing when you do these ones is you're setting up VLANs that separate all of my video streaming stuff is sitting here on the network. My PC doesn't care what that is, doesn't want to see it, doesn't need to know what it is. My printer, anything else that's on my corporate network, my FPOS machines don't care about that stuff. So I'm isolating all that traffic over here. I'm dealing with my layer 3 switch and all its brain power to deal with switching and moving all that traffic and doing, it's like the duck on the water. Looks smooth and looks natural, but underneath the feet are going like crazy. That's what's happening over this side of the network. As far as the rest of it's going, I've got all the rest of whatever bandwidth's in there and whatever network switching's left to be able to deal with all my other devices and make sure they move smoothly. It's the rough version of how that works. Anybody who wants to do one of those video over IP systems, whether they're ours or Bluestreams and the rest, tell them to have a chat to us about it and sort of design it up properly and make sure it works, because it's not as simple as just plugging in and going, in most cases anyway.
So in relation to CCTV, what would you feel necessary to do a VLAN? So high bandwidth cameras, a lot of resolution.
Yeah, so cameras are an odd beast, because a basic 2 megapixel IP camera can stream anywhere from a couple of megabits per second when it's running a H.265 plus doubly, whatever, encrypted, not encrypted, compressed system, or it might blow out to 15, 18, 20 megabits per second if it's motion JPEG uncompressed, but the best quality video you could possibly do. So you really got to have a look at how much traffic your cameras are generating first, and then work out where that's going to go. So the motion JPEG example is a good one. When you're dealing with something like license plate cameras or front door cameras or something where you really want to see every detail of somebody that's coming in, motion JPEG will do that for you, but it's hugely bandwidth intensive. It's basically taking static images and not doing anything to change from one to the next one except just stacking them on top of each other to turn it into video. Whereas a H.264 or 265 or one of the other compression ones looks at what changes in the images, or it uses algorithms to work out what happens between this image and the next one, removes the bits that it doesn't care about because they're the same, and then just pushes the other stuff through. It's why you get not jerkier footage, you get footage that looks slightly smeary or odd when you're trying to pause it, because you're kind of going between one frame that's kind of the same and another frame that's not quite the same but almost, so on. Looking at those, looking at the bandwidths and choosing that based on the cameras and overall, and then you'll go, right, I need to put this onto a VLAN or not. So that's the long-winded way of doing it.
So it's best to analyze it.
The short version of that is, if you're dealing with a lot of 4K cameras, like 8 plus 4K cameras, you might want to start looking at it. With a lot of the NVRs, they have ports on the back of them that aren't actually connected to the rest of the network. They do their own internal network and then only stream some of the traffic out to the rest of it. So like the non-eco versions of all of our NVRs will handle 4 or 8 or however many on the back of the unit itself, do all the switching, do everything else like that internally to be able to record the footage, and then have one Ethernet connection out to everything else on the network. And so each of the cameras only talks to this. They don't talk to the printer, your computer, the router, or anything else like that along the way. So that can isolate the traffic, and most manufacturers do that to try and avoid those sort of issues. But in my house, I can't plug them all in directly because I've got too many for the number of ports on the back of my machine. So I have Ethernet switches, and I have PoE switches. So I have some cameras that run via the network, some run the NVR, and I need to keep an eye on the traffic so that I don't drop out the Netflix streaming on a Friday night just because the cameras are running. So yeah, those programs and the software can help you work out what's going on with your traffic. The NVRs have got it built in as well. When you're recording or when you're streaming the cameras to it, go into the streaming settings, you can actually see the bandwidth it's actually chewing up per camera and via the network switch as well. Okay, yeah, long-winded way of saying probably 8 or more 4K cameras, I'd say would be a minimum that you'd want to start looking at something like that. And everybody should have layer 2 switches at home just because it's fun and you get to play around with some faster switching as well. Not that expensive. TP-Link ones start at about 120, 130 bucks to do sort of some basic, quality of service and other things for yourself. So, worth trying. Cool. Anything else? No problem. All right. As I said earlier at the start, I've got a PDF version of this. So if you want that for your records or for anybody that wasn't here, more than welcome to. For the guys online, we'll upload it so you can download it afterwards as well. And I might try and tweak it to add a few extra bits and pieces that we were talking about as we went through. Okay? Cool. Thank you very much for your time. Appreciate it.